this tutorial on multi-objective planning under uncertainty. My name is Shimon Whiteson, and this is Diederik Roijers. We're from the University of Oxford, and we will be presenting the tutorial. Let me start by giving you an overview of the schedule. So I'll be giving the first half of the tutorial, which is basically a motivation for multi-objective planning and some foundational concepts. And the second half will be done by Diederik, and he's going to give you an overview of some state-of-the-art methods for multi-objective planning, and also tell you about some applications. So halfway through there is an official coffee break of half an hour, and each half will also be informally divided into two, so you guys can have a 10-minute break in the middle, so we don't overwhelm you with too much information in one go. So as Diederik wrote on the board, you can find the latest version of the slides online if you want to follow along. If you're interested in knowing more details, I encourage you to take a look at our JR survey article from 2013. This tutorial is pretty closely based on that survey article, so if you want to look up any details or think more about it later, that's a good place to start. Also, Diederik recently finished his PhD thesis, which is also available online, and a lot of the same content is in there also, but in much greater detail, so that can be considered the authoritative reference on the material presented today. Okay, so let's go ahead and get started with part one, the motivation and concepts. Unlike a lot of other areas in decision-theoretic planning or in artificial intelligence in general, the motivation for multi-objective planning is actually not totally obvious. And when I talk to people who haven't studied multi-objective planning before, I often encounter misunderstandings about what the goal is or what the motivation is. So I want to start by making the motivation really explicit so that everyone is on the same page about what it is that we're trying to do and why it makes sense. So let me just start with a few examples. Here are some scenarios where you might find it natural to think in terms of multiple objectives. So let's suppose you're in need of medical treatment, and you have a bunch of different treatment options that are available to you. And they might vary in quality with respect to more than one objective. So for example, one objective might maximize your chance of being cured, but there might be another objective, another treatment option which minimizes your chance of having side effects or dying. How are you going to weigh these different objectives and decide which treatment is actually best for you? Or another example, let's suppose you want to build an autonomous agent that's going to help coordinate traffic in some city by controlling the intersections in some urban area, the traffic lights at some intersections. So you might want to minimize latency, you might want to maximize throughput, you might also care about things like fairness, that all drivers are treated in the same way. You might also want to minimize environmental impact or noise. There are many objectives that you might care about when you model this from a decision-theoretic perspective. Here's another simple example which we actually use in some of our experiments and which will come up again later in this tutorial. So imagine you own this mining company. You have a bunch of mines in the mountains. And in each village, there are some workers, and every day you have to decide which workers to send to which mine so as to maximize something. But you can mine different commodities. So for example, you can mine gold and silver. And you might care about how much of both of these commodities you get. So you can view this as a problem that has two objectives. Here's an even simpler example, and I included this example because this is a sort of like toy problem you typically see in reinforcement learning. You've got some robot in a grid world, and it can move around, and it's trying to get to the treasure. But every time it moves, it incurs some cost. It uses some electricity, so it gets -1 every time it moves, and it gets some jackpot when it gets to the goal. The reason I included this example is that even though this is one of the simplest possible decision-theoretic problems, and you typically think of it as having one objective, which is to maximize some reward function, it actually decomposes nicely into two different objectives. So you want to minimize the battery power that you use as you move, but you also want to get the jackpot. So even here, it's not obvious that this should be a single objective. Okay. So we've seen some examples of problems that can be naturally modeled as having multiple objectives. But that in itself does not imply that we actually need new models for multi-objective problems or new algorithms for solving those problems. So some people actually explicitly argue that we don't. So Rich Sutton, who literally wrote the book on reinforcement learning, formulated what he calls the reward hypothesis, which says all of what we mean by goals and purposes can be well thought of as maximizing the expected value of the cumulative sum of a received scalar signal. And that word scalar is obviously very important for our purposes. So let me just try mathematically to describe what the reward hypothesis is saying. So here we have capital Pi. This is a set of possible policy solutions to your problem. And it's being mapped to some scalar reward. So every policy has some value, and that value is a scalar. It's a real number. And so the value of some policy can also be written as the expectation of the sum of some immediate reward signals. So maximizing the expected value of a cumulative sum, as it says in the reward hypothesis. And then the optimal policy is the one which maximizes this value. So there are many things about the reward hypothesis that one could object to. So you might say, for example, maybe we don't care about maximizing expected value because we want to be risk sensitive. Or we might say, oh, the rewards actually don't decompose as a sum. But the objection that I'm going to raise is to this word, the scalar signal. So obviously, in order to motivate multi-objective models and multi-objective algorithms, we're going to need to try to rebut the reward hypothesis. We're going to say there are situations where the best way of modeling what we're trying to do is not as a scalar signal, but as a vector. So there are two parts to this argument. There's what I call the weak argument, and then there's the strong argument. So the weak argument is the argument that I was already implicitly making when I showed you these examples of problems that are naturally modeled in a multi-objective way. So the weak argument says simply, real-world problems are multi-objective. So this is the same as the formalization I showed you on the previous slide. The only difference is that now every policy in this set of policies is being mapped to a vector of rewards instead of to a scalar. So I'm using bold here to indicate vectors. So I now have a vector-valued value function. Every policy has a vector that corresponds to its multi-objective value. So hopefully those examples I showed you at the beginning already convince you that this is, in many real-world settings, an intuitive way to model the problem. But the reason that this is called the weak argument is because this is by itself not enough. So the devil's advocate might come along and say, okay, you might naturally model this problem as multi-objective, but that doesn't mean that you need new models or new algorithms. You could just take this multi-objective problem and scalarize it. Now what do I mean by scalarize? The scalarization function is something that's going to project this multi-objective value down to a scalar. So I'm going to design some function f, and this function f is going to describe how this multi-objective value can be projected back to a scalar value. And then I can just use all of my original solution methods, and I don't need to do any new research. So this is the scalarized value. And it's the output of this scalarization function f, which takes as input the multi-objective vector value, and it's parameterized by some vector of weights. So the scalarized value depends on those weights, and that's what this problem is. So a simple example, which is one we'll talk about a lot today, is the linear case. So a linear scalarization function just takes each value in the multi-objective value and multiplies it by some weight, and then sums those weights. So this is the inner product of the multi-objective value and the weight vector. So what this scalarization function does is it gives us an a priori prioritization of the objectives. Before I've solved the planning problem, before I've figured out what solutions are available, I'm already going to say how important the different objectives are to me. And if I can do that, I can convert the problem back to a single objective one, and then I won't need any new methods, we won't need to do any new research, we could end the tutorial right now. Okay, so this is the objection to the weak argument. So the response to that, so what this shows us is that the weak argument is necessary but not sufficient. If there weren't any real world problems that were naturally modeled with multiple objectives, we could just stop right there. But having such problems is not enough to justify developing new methods because of this rebuttal from the devil's advocate. Okay, so how do we respond to the devil's advocate? We respond with a strong argument. And the strong argument says, essentially, a priori scalarization is sometimes impossible, infeasible, or undesirable. And in such settings, it's very useful to have methods that don't commit a priori to some scalarization, but instead are going to produce a set of possible solutions, each of which could potentially be optimal depending on what scalarization later was selected. So this is a coverage set of undominated solutions, which we'll define formally a little bit later on. So let's look at a few different scenarios that illustrate why it is that you might not want to commit a priori to a scalarization. So the first scenario is what we call the unknown weight scenario. The idea here is that the weights of the scalarization function will be known when you have to execute the policy, but they're not known at the moment at which you have to do the planning. So when you're doing the planning, you're not ready to commit to a particular scalarization function, so you need special methods that will give you this covered set, so that you can later choose from that covered set when the weights become known. So that's what's shown in this figure. We have our multi-objective decision problem. We feed it to our planning algorithm, which produces a covered set. Then later, after planning is complete, the weights of the scalarization function are revealed to us. Now we know the scalarization function. We can use that to select a single policy from the covered set that we computed, and then we act according to that policy. The second scenario is what we call the decision support scenario. So this is quite similar to the unknown weight scenario, but the thing is these weights are never actually explicitly revealed because they may not explicitly be known to anyone ever. They may just, for example, exist implicitly in the user's brain. So the idea here is that if a human user is in the loop, if the human is the one who's actually going to decide how the system behaves at the end of the day, the human may find it difficult to quantify a priori how important each objective is. So, if you think about this medical treatment example, and I say, okay, you go to the doctor and the doctor says to you, okay, in order to select a treatment plan, you have to tell me how much more important is it to you to be cured versus avoiding side effects. Is it 2 times as important? Is it 2.4 times as important? You have to choose a number. Can you do that in a meaningful way? Most people would find that very difficult. But if instead the doctor says, okay, I've computed a set of solutions, a set of treatment options to you, all of which could be reasonable depending on your priorities, and then you look at them and say, okay, which one of these seems to fit me best? That's something that most people couldn't do. This is what we call the decision support scenario. It looks almost exactly the same. We have this multi-objective decision problem. We feed it to our planning algorithm. It produces this covered set. But now, instead of the weights being explicitly revealed, the user just looks at the covered set and selects a policy according to his own idiosyncratic preferences, which, if you like, you can think of as corresponding to some weights that are inside that user's brain, but we never explicitly know what those weights are. And then, we just execute the policy selected by the user. Yeah?
Is this somehow related to that analytical, hierarchical process or something like this? Are you familiar with that?
No, I'm not familiar with
that. It's a crazy framework, so to say, where you basically have a situation like this. You have a set of parameters and you have to select which order they have in terms of importance, so to say. Mm-hmm. And this method somehow helps you to find out what's the gap, what's the ratio between each pair of parameters. Sounds similar,
so here we're not getting to any particular way of doing the selection. So the selection could, for example, be done by showing pairs of policies to the user, and the user says, I like A better than B. And then after a number of such interactions with the user, you might be able to deduce a single policy from the covered set. This is basically a black box. You can do this however you like. The premise is just that it's going to be easier for the user to select a policy if the covered set has already been computed than a priori to be asked, what are the weights of your scalarization function? Okay. And the third scenario is what we call the known weight scenario. So this is a scenario where we do actually know the weights in advance at the moment in which we do the planning. So in principle, we could plan in a single objective way because we know the weights, so we can convert the problem to a single objective one. However, in some cases, that conversion process will yield an intractable problem. So I'm not going to talk about this a lot in the tutorial, but there is a slide later which revisits this idea in a little bit more technical detail. But for now, the point is just that some properties that your planning algorithm depends on, for example, what was mentioned in such a reward hypothesis, that the value you're trying to maximize decomposes as a sum, that property could be destroyed by the scalarization process. And you'll be left with a single objective problem, which is much harder to solve. So even though you could in principle scalarize, you choose to solve it in a multi-objective way because it's more tractable. So summarizing the motivation. Multi-objective methods are useful because many problems are naturally characterized by multiple objectives, that was the weak argument, and cannot be easily scalarized a priori, that was the strong argument. Okay, so one more comment I want to make about the motivation is written here. So sometimes when I've talked to people about multi-objective planning and other kinds of multi-objective decision-making, they've said something to the effect of, look, these single objective models are already hard enough. Like we have so many problems in terms of scalability and tractability with single objective decision making. How can you justify this more expansive model that's even more complex, that's even more computationally expensive to solve? And while I understand the reasoning behind that question, I think it's a fundamentally backwards way to think about it. So I think, actually, if you want to take a problem which is naturally modeled as multi-objective and convert it to a single objective one through a priori scalarization, the burden of proof rests on you to justify that a priori scalarization. And that's not to say that you can't meet that burden of proof. So I'm not here to tell you multi-objective planning is a hammer that's right for every nail. I think there are many real-world situations where you should do single-objective planning, either because the problem is inherently single-objective or because it's naturally multi-objective, but this a priori scalarization is totally reasonable. You have enough information, or approximately enough information, to do this scalarization in a reasonable way. In which case, you should go ahead and do it and use your single-objective planning methods because it will be more efficient. However, the burden of proof is on you to justify that model. If you have a problem that naturally has multiple objectives, you should start from the premise that we should solve it with multi-objective methods and switch to single-objective ones only if we can meet this burden of proof. Okay. So that was the motivation for multi-objective planning. So now I'm going to give a bit of background about MDPs and multi-objective MDPs so that we can talk more precisely in later parts of the tutorial. Then I'm going to present a problem taxonomy, which is kind of an overview of different kinds of multi-objective planning problems. And then finally, we're going to fill in the taxonomy by talking about different solution concepts that are suitable for different areas of the taxonomy. So let's quickly just go through some background. So I'm basically assuming that all of you already know what a Markov decision process is, but this is just so you can get used to the notation that we use. And then I'm going to describe the multi-objective variant of it. So a Markov decision process, we have states and actions. We have a transition function which determines how the state evolves over time. We have some reward function. And we have a probability distribution over the initial state. We also have a discount factor, so we're doing infinite horizon planning here, which says how important immediate versus future reward is. Okay, so in this Markov decision process, we're typically interested in maximizing expected return. And expected return is typically assumed to be additive, so it can be written as a discounted sum of the rewards that we accrue over time. And we're going to maximize expected return by finding some policy. And in particular, a stationary policy is one that conditions only on the current state. So this is a stochastic but stationary policy. So it maps states basically to probability distributions over actions. And we can also consider the deterministic variant of the stationary policy, which just maps the states to actions, doesn't condition on anything else. Okay. So we can think about a few different kinds of value functions. So the value function tells us the expectation over this return that we're trying to maximize. So we're going to distinguish between a state-independent value function, which specifies the expected return when following pi from some initial state. So this is the return starting from the initial state 0. And a state value function, which is the value function that is probably most familiar to you, which conditions on the current state. So this is the expected return, given that we're using some policy and that we're currently in some state S. So, of course, the Bellman equation tells us that we can restate this expectation of the value function recursively, given that we have a stationary policy. So we can rewrite this value function as an expectation over, so we marginalize out the action that is selected by our policy, and the next state that we reach through our transition function. And then the return decomposes as a sum of the immediate reward and the discounted value of the next state that we arrive at. Okay. So a well-known result about these stationary about additive single-objective MDPs is that there always exists a deterministic stationary optimal policy. So we can use stochastic policies if we want, and there may even be stochastic policies that are optimal, but we know that there always exists at least one deterministic stationary optimal policy. Okay, and all optimal policies share the same optimal value function, which can be written in which can also be written recursively using the Bellman optimality equation. And once we know this optimal value function, we basically solve a problem because we can extract an optimal policy from it using local action selection. So local action selection means we just, in every state, select the action which maximizes the expected return according to this optimal value function. So this equation is computing a one-step look ahead just thinking about the next states we could reach and what the optimal value function says about those next states and what that means the expected value of the considered action would be. Okay. So that was the whirlwind tour of Markov decision processes. So let's think about the multi-objective variant of this. So really the only thing that changes is the definition of the reward function. Now, instead of mapping a state and an action and a next state to a real number, we're mapping it to a vector of real numbers. So R here is in bold to indicate that the output of the reward function is a vector. And we can also now define a multi-objective value function. So this is the expected value of this vector. So we're just summing these vector valued rewards over time. And so this is the state independent value function, and then this is the state value function. It's the same idea, but now we're just conditioning on the current state. Okay, so what are the complications that are raised by having this vector valued reward function? Well, it means that this vector valued value function now imposes only a partial ordering. So you can easily imagine a scenario where you say, look, I've got two policies, pi and pi prime, and policy pi is, for a given state, policy pi is superior with respect to objective I, but inferior with respect to objective j. So the fact that we've made the reward function, therefore the value function, vector value means that the definition of optimality is no longer clear. So we're going to have to develop some new notions of optimality. Okay, so we're going to do that by constructing a problem taxonomy. That's going to tell us, that's going to sort of divide the space of possible multi-objective planning problems into some different categories, and then for each one we'll think about what the correct notion of optimality is. Okay, so to construct this problem taxonomy, we're going to take what we call the utility-based approach. So if you look at the literature on multi-objective planning, or all literature on multi-objective decision-making, it typically takes what we call an axiomatic approach. And the axiomatic approach says basically, we define the optimal solution set for a multi-objective problem to be the Pareto front. And I'll define the Pareto front exactly later. It's something that most of you are probably familiar with. In the utility-based approach, we're going to take a slightly different approach. We're going to try to, instead of just assuming this optimal solution set is the Pareto front, we're going to try to derive an appropriate solution set from more fundamental principles. So the reasoning behind the utility-based approach goes as follows. It says, look, at the end of the day, in the execution phase, we can only select one policy. When we finally act, it's going to be according to one policy. And presumably, if whoever selected that policy is a rational agent, then presumably that policy was selected because it maximized some scalar utility. So that scalar utility can be thought of as a scalarization of the vector value, multi-objective value, according to some scalarization function that's parameterized by some weights W. And those weights W may be hidden or implicit. Maybe they weren't known during the planning phase, or maybe as in the decision support scenario, they're never actually known. Nonetheless, we posit that in a sort of Platonic sense, they exist. So this, whoever selected this one policy that we end up using when we act, was behaving optimally, was selecting the policy that maximized this scalar value where scalarization was done according to some weights W, whether we know what they are or not. Okay, so what does that imply then about the planning phase? If in the planning phase we don't know what W is, then what should we do? We should try to find a set of policies that contains an optimal solution for each possible W. We don't know what W is, but we know that the policy will be selected according to some W. So we're going to cover every eventuality. We're going to try to find a set of policies so that no matter what W is, there's a policy in that set which is optimal for that W.
What are you assuming about W? Are you making some kind of assumptions about W? Because, well, how large can be this space?
I'm not making any assumptions yet, but I will make those assumptions, and those assumptions will delineate areas of the taxonomy. Now I'm just speaking very generally. Okay. So if I don't know what W is at planning time, then in general this set will contain more than one policy. And it's that set of policies that I want to compute. Okay. So given this premise, we can then deduce what the optimal solution set is by looking at three different factors, three different properties of the multi-objective problem. And those are listed here. So actually, I'll just go ahead to the next slide because they're described in more detail.
Excuse me?
Yeah.
Does it mean that in the end we could select a policy that is not Pareto optimal?
I'm not a,
be surprising.
I'm not aware of a way of a choice that you could make about these properties that would yield a solution set which is bigger than the Pareto front. But you might get a solution set which is smaller than the Pareto front. So the Pareto front might be overkill. Did you want to answer?
No.
Okay, so let's look at these three different factors. So the first factor is which multi-objective scenario are we in? So in the known weight scenario, we're going to be looking for just a single policy, just as we are in a single objective planning. And in the unknown weights or decision support scenarios, we're going to be looking for multiple policies, because we want to cover all the possible weights. And from once we get down to actually nuts and bolts planning, the decision between unknown weight, the difference between unknown weights and decision support kind of goes away. We treat them the same from a planning perspective. Okay, so that's the first property. The second property is what does the scalarization function look like? So we might not know the weights of the scalarization function, but we might know some properties of it. So for example, we're going to talk a lot about the special case of a linear scalarization function. Or if it's not linear, we're going to make a weaker assumption, which is that the scalarization function is monotonically increasing, which I'll define later. And then the third factor is what kind of policies are we going to allow? Are we going to insist on deterministic policies, or are we going to permit stochastic policies? And those are all going to affect the solution concept that we end up choosing. Okay. So this brings me to the, how am I doing on time? This brings me to the problem taxonomy. And so this is a slide that you're going to see a lot of in the coming half hour or so. So you don't need to parse it all now because I'm going to step you through it box by box. But for now, the main thing to understand is that these three factors that I've already mentioned, they're described here on the axes. So here we have the nature of the scalarization function. Is it linear or just monotonically increasing? And then here we have which scenario am I in? Do I only need a single policy because it's known weights? Or do I need multiple policies because it's unknown weights of decision support? And then am I looking at deterministic or stochastic policies? And then in each of these boxes, we have the correct solution concept for the corresponding scenario. So what I'm going to do in the rest of the first half of this tutorial is step through this taxonomy. For each of these boxes, we'll derive that correct solution concept. Okay. So let's see. This is kind of a natural breaking point. So yeah.
When you say non-stationary policy, you mean that it would depend on the amount of objective I've already paid so far, or is it with respect to time in a different way?
So we define a stationary policy as one that conditions only on the current state.
Yeah.
So then a non-stationary policy would be one that conditions on anything else, the most common thing being time. But you could imagine other things that you might also condition on.
Time doesn't make sense because, it does make sense possibly, but I'm guessing that the reason it varies with time is because up until now we have paid different amounts of objective in execution. Is that the key reason why it varies with time? Or?
So actually I think even if you didn't, well...
No, because you will probably go through it and ask some questions.
But we're a little bit ahead of schedule, so there's plenty of time to discuss.
I was just wondering why should it be non-stationary?
So I think even, because there are situations where you might prefer a non-stationary policy that conditions on time, but doesn't condition on how much value you've gotten in a particular objective. So we'll see later a clear example where, under certain assumptions, a stochastic policy is preferable. But imagine stochastic policies are forbidden. You can kind of mimic a stochastic policy with a non-stationary policy that, like, if t is even, does this, and if t is odd, does that. It would mimic a stochastic policy that with 50% probability does the two different things.
If you're willing to mimic, then I would simply say that put time in the state space and then every non-stationary policy is stationary.
Yeah, sure. Of course. What is stationary and non-stationary depends totally on your definition of the state space. So, yeah, convert between them. Great question. Other questions?
Can you put back slide 19? Slide 19. Just, yeah. just want to make sure I'm not lost in the notations here. So, am I true in believing that first bullet point when you try? Okay, so V is a vector of value functions. Okay.
Yes. Yes.
And so big, little r, I guess. Okay.
So everything in bold is a vector. So this is a vector of immediate rewards.
Okay. All right. So basically, yeah. Okay.
So we're just doing like the vector sums here.
Yeah. Okay. Yeah. Done.
Okay. Yeah.
You mentioned that fixing a specific weight function will give you an intractable problem sometimes, whereas keeping it in an arbitrary weight space is more tractable apparently.
Yeah.
Can you go into a little bit more detail?
I will later, but just to give you a preview, so this additivity property is very important for planning methods that depend on the element equation. So to decompose the value in this recursive way, you need the return to be additive. You need to be able to write the return as a sum. If you have a nonlinear scalarization function, then applying that scalarization function may destroy that property. So then you'll have a summation for the expectation, you'll have a summation for the additive return, and you won't be able to push the scalarization function inside.
I thought you mentioned that having a specific weight function would make it intractable, but you are actually saying that the projection is given. It's a fixed projection, so it comes also with the weight function, not just constants first. I think
scalarizing, it's the scalarizing which will destroy the property. Yeah. Okay, great questions. So I propose we take a short break now, 10 minutes, and then we'll do the taxonomy starting at 2:40. Okay? And deriving the solution concepts for each box in the taxonomy. So we're going to start at the top left and move across, and then we'll do the bottom part. So the easiest case we're going to consider first is if the scalarization function is linear and if the weights are known. And for now, we're going to ignore whether the policies are allowed to be stochastic or not, because that's not going to be important until later. Okay, so as I mentioned before, an important special case of the scalarization function is when it's linear. And this means that the scalarization function just computes the inner product of the vector value function and the weight vector. So intuitively, each element of this weight vector is quantifying the importance of the corresponding objective. So this is very simple and intuitive scalarization function. So for example, in many situations where ultimate scalar utility corresponds to money, then you can think of it as a linear scalarization function. Like imagine you have a recycling robot that can collect cans and bottles. Well, ultimately it wants to maximize revenue, and that can be written in the following way: the number of cans it collects times the price per can, plus the number of bottles it collects times the price per bottle. So the price per can and the price per bottle, these are the weights of our scalarization function. So if we know those weights, then it's easy to determine the scalarization function. Okay, now for reasons of mathematical convenience, we typically constrain the scalarization function to be not just a linear combination, but to be a convex combination. So we're going to assume these weights are greater than 0 and that they sum to 1. So in our recycling robot example, that would just correspond to normalizing the weight values by the sum of the weights. So the reason why this is useful will become apparent later. Okay, so now consider the setting at the top left of the taxonomy. We have a linear scalarization function, and we're in a known weight setting, so we're just looking for a single policy. So we know these weights in advance. We know the price per bottle and the price per can. So this is the one setting in the taxonomy in which no special methods are required. So what we can do is just apply our scalarization function to each reward vector. So we can do this because the inner product distributes over the addition, yielding a normal MDP, right? So this is our scalarized value, and because we have a linear scalarization function, we know that this is an inner product. And this second term in the inner product is itself an expectation. This is just the definition of the vector value function. And because this summation and this expectation, because they're linear, we can just move the weights inside. That's what's happening here. By moving these weights inside, what we've basically done is just define a new MDP, a single objective MDP, where the scalar reward function is itself just an inner product of the vector value reward function we were given in the multi-objective problem definition, Just the inner product of that and the weights. So this gives us an ordinary single objective MDP. We apply standard methods to it. We get a deterministic stationary policy, just like we always would, and we're done. Okay. So that was the top left corner. So this is the only box in the taxonomy where we won't need any special methods. So, you know, an example like this recycling robot, it's realistic to think in many settings that before you do the planning for the robot, you might already know what the price per can and price per bottle is. So you know the weights, you can do the scalarization, use a single objective method, and get on with your life. Yeah?
One potentially stupid question. One of the hypotheses you had for this case is where you assume that things have to be complex. It has to be a convex combination. What happens if you have, for instance, an knapsack constraint on this? Can you have this kind of scenario? And if you have something like this, does it change the analysis at some point or not?
So,
I don't know how important this is.
so you're saying, suppose my weights were not convex.
Yeah. Let's suppose that you don't have something between 0 and 1. You just have a weight for your whole.
So the argument that I made so far about being able to convert to the single objective problem does not require them to be convex. I'm going to use that later. But in general, I think because you can enforce this property by just normalizing, I think, you know, all that's going to do, whether you normalize or not, is just going to affect the magnitude of the single objective scalar value that you end up with after you perform scalarization. So in that, you know, at some point that becomes arbitrary. Like I can define an MDP where rewards are 1, or I can define the same, you know, an analogous MDP where all the rewards are 1,000. It's essentially the same MDP. But I haven't used this property yet. Okay, so that was the easy one. Right, so as I said, this is the only cell in the taxonomy that doesn't require multi-objective methods. So let's move to the top right now. So let's suppose we still have our linear scalarization function, but now we're in the unknown weights or decision support scenario, so we're really looking for multiple policies to cover all the possible weights. Okay, so the solution here is going to be what's called a Convex Covered Set, and I'm going to define that in a minute. Okay, so when we're in one of these scenarios where we need multiple policies, we're assuming that during the planning phase, the weight vector is unknown, so the size of the solution set is generally going to be greater than 1, because we're going to need policies to cover all of the possible weight vectors. So what does planning mean in such a setting? Basically, we can think of planning as a pruning process. So rather than normally we think of planning as, okay, we have all these possible policies, we're going to find the one that's the best. Now we're going to think of planning as, we have all these possible policies, and we're going to prune away all the ones that couldn't possibly be the best. We, in general, won't be able to reduce it to 1 because we don't know what the scalarization weights are. But we want to get rid of those that couldn't be optimal, regardless of what W was. So planning becomes a pruning process, and we want to end up with a set of policies that could potentially be optimal. So let's develop some terminology that's going to allow us to express that formally. So the first notion is what we call an undominated set. So the undominated set is the subset of all policies for which there exists a W for which the scalarized value is normal, is maximal. So this capital Pi is a set of all policies. An undominated set are those policies that are in that set and for which there exists some weight where at that weight, that policy has the maximum scalarized value. So we can think of that weight as being the justification for that policy's right to exist in the undominated set. If you want to be in the undominated set, you should be able to point to some weight where, hey, I'm the best for this weight, therefore I get to be in the undominated set. So a closely related idea is what we call a covered set. So the undominated set basically describes what we want, but it could be a little bit overkill. So there might be things in the undominated set that we actually don't need because they're covered by other policies in the undominated set. So to express that distinction, we have the covered set. So the covered set is in general a little bit smaller than the undominated set. It's a subset of the undominated set. Such that for every weight, there's a policy in the covered set with maximal scalarized value. So it's called the covered set because it covers every weight. For every weight, we've got a policy that covers that weight by being optimal with respect to that weight. So it's a subset of the undominated set with the property that for every weight, it has a policy that's in the covered set and which is optimal given that weight. Okay. So here's a simple example to make this idea clear if it wasn't already clear. So here we have a very simple problem where our scalarization, we have just one scalarization weight and it's binary. So the space of possible scalarization functions has two members. So the scalarization weight could be true or it could be false. Now note, I'm not actually saying anything here about how many objectives we have. I'm not saying we have 2 objectives. We could have any number of objectives, but our scalarization function allows only 2 possibilities, true or false. Okay? And we have a set of 4 possible policies. And for each policy, we have a different value depending on which scalarization function we use. Okay? So in this setting, we can easily see that the undominated set consists of policies 1 through 3. Because for each of those policies, is optimal for at least one of the weights. Right? You can see each of those 3 policies has maximal value at one of the weights. However, we can construct a covered set using only 2 of those 3 policies, because there are only 2 scalarization weights to cover. So we can cover it using pi1 and pi2, or using pi2 and pi3. So the covered set is a subset of the undominated set that still covers all of the weights. And typically the weights are continuous, but in this trivial example, they were binary.
So does the covered set has to be minimal, or
No.
not necessarily, right?
So right. So let's see. So it's a subset, but not necessarily a strict subset of the undominated set, and there could be many covered sets which satisfy this property. But what do we want from a planning algorithm? We wanted to find a minimal covered set. Yeah?
Just for clarification, the undominated set can be empty?
I don't think so. Unless capital pi is empty, I don't think so.
Well, you mentioned before they specified that the partial order, and this is a
Maximum.
V is a function as well, right?
Yes,
It's
maximum.
not just the weights themselves. Do you have any assumption on V? Is it linear?
No, it's just a value function.
So,
It's maximum. So maximum.
So I don't see how it could be empty.
Even if it's a partial order, there's always a maximum element.
I mean, like these are scalars now, right? These value functions are scalars. The V is not in bold. W is in bold because the weight vector is a vector. But this is the scalarized value. So once I've selected W, I have a scalar value. And
okay.
for any weight, there's some policy must have the highest value. Sorry for the notations a bit confusing.
I didn't get why there are 2 covered sets. It's a subset, so why 2 covered sets?
Why are there 2 covered sets?
Still possible coverage set.
So look at this example.
No, but it's 2 CSEs. Okay.
There are actually 3 coverage sets.
There are 2 different ways to cover all the weights.
There are 3.
You can also use U
Oh,
itself.
okay. Well,
Yeah, you can also use U.
Yeah. U is also a covered set. There are 2 minimal covered sets, and there's 1 non-minimal covered set.
okay.
Do you have some non-trivial lower bounds for the minimal covered set? You need at least 1. That's clear. Apart from that, can you say more?
For the number of covered
Yeah, the minimum size.
I don't think so, because you could have a problem where there's a policy which is best for every weight.
Yeah.
Do you have an upper bound?
The whole capital I. Capital I. It could be that you need every possible policy. So this pruning process might not find anything to prune. That's the worst case.
Even in the worst case.
Yeah. No. In the worst case, it might find nothing to prune. Great question, guys. Okay. So we've defined this covered set. So in the execution phase, we're going to select a single policy from this covered set and execute it. In the unknown weight scenario, the weights are revealed to us, and then we can select this maximizing policy just by computing this argmax. Right? So now we know the weights, so we can define the scalar value of every policy on a covered set. We just select the policy which maximizes that scalar value. So you might notice this looks exactly like the original planning problem. The only difference being that now we've replaced pi with CS of pi. So if you think about it, that makes sense, because now we're thinking about planning as a pruning process. So the idea is that at execution time, we're going to have to compute this maximization. And the more we can prune during planning time, the easier that maximization will be. So in this worst case that you mentioned, CS pi will equal pi, and this selection phase will be as difficult as the original planning problem. And that's, yeah. Then multi-objective planning has nothing to offer. But in practice, the coverage set is way, way smaller. And then decision support, the same thing happens, but implicitly. So the coverage set is just manually inspected by the user, and he selects whichever policy he likes, potentially by performing something like this in his head. Okay. So now we formalize this notion of an undominated set and a coverage set. So now let's make these notions more specific to the current setting in the taxonomy we're looking at. So we're in the top right corner. So we're considering a case where the scalarization function is linear, but now we need multiple policies because we don't know W at the time of planning. Okay, so the analog to the undominated set, when we have a linear scalarization function, is the convex hull. And here's the definition of the convex hull. It looks exactly like the definition for the undominated set. The only difference is that the scalarized value is now explicitly written as this inner product. But just as before, it's a set of all policies, such that for that policy, there exists some weight where that policy is maximal. But maximal now means according to a linearly scalarized value. This is just a special case of an undominated set. And the analog to the coverage set, when we have a linear scalarization function, is the convex covered set. So again, this is exactly the same definition as before. So it's a subset of now the convex hull, such that for every weight, we cover that weight. So there's something in the convex coverage set, such that, which is optimal for that weight. But now again, optimality is explicitly defined using this inner product because the scalarization function is linear. Okay, so in this setting where we have a linear scalarization function and we need multiple policies, the solution set is going to be this convex coverage set. So we can visualize this notion using in a couple different ways. This figure is very important for intuitive understanding, and figures like this will appear throughout the rest of the tutorial, so this is an important slide. So there's two ways to visualize it. Let's start by just focusing on the left-hand side. This is objective space. So imagine we have a problem with two objectives. So we have one objective on the x-axis and the other objective on the y-axis. And each of the points in this two-dimensional space corresponds to a different policy. And the location of that point indicates the multi-objective value of that point. So if I take this point, I can say, okay, this point will give me 2 in the first objective and 1 in the second objective. Okay. Now the convex hull corresponds to the red and the blue points. And the convex coverage set corresponds to just the red points. So the blue point is something that's in the convex hull but not in the convex coverage set. Now how do I know that? How do I know which points are in the convex hull and which ones aren't? We can see that by looking at weight space. So this is where we're going to make use of the assumption that the linear scalarization function computes a convex combination and not just a linear combination. So here on the x-axis, I'm talking about weight space. So each point on this x-axis corresponds to a different scalarization function. Now because I have two objectives, that weight vector will have two values, but because of the convex assumption, one of them is going to be 1 minus the other, right? So W0 equals 1 minus W1. So on the x-axis I've just shown W1, and W0 is implied by it, okay? Now on the y-axis I'm showing the scalarized value of each of the policies. And that scalarized value will correspond to a vector. So here I have, if I put all of the weight here, that means I care only about one of the objectives, so the value of the policy is going to be the value of that policy in that objective. And similarly here, this is the value of the policy in the other objective. Because the scalarization function is linear, the value will change linearly as for all the in-between weights. Okay? So each policy now corresponds to one of these lines. And the convex hull corresponds to the undominated upper surface. And you can see the blue line it contributes to the undominated upper surface, but I can represent that undominated upper surface without the blue line, because it's only optimal in this one point, which is already covered by these other lines. So if you know anything about POMDP planning, a lot of what I just said is probably very familiar to you. These are exactly the same ideas that are used in POMDP planning. And the relationship between POMDP planning and multi-objective decision-making is something that people have thought about for quite a while. I think, are you going to talk about that? Diederik will come back to that briefly later. But yeah, we can think of multi-objective planning as POMDP planning where the hidden state corresponds to the weights of the scalarization function, or can be represented easily. That does not lead to efficient planning methods, but a lot of multi-objective planning methods do steal ideas from POMDP planning because of this insight, because they share these key properties. Okay. Okay, so what we've seen so far then, if we need multiple solutions and our scalarization function is linear, the right solution concept is going to be this convex covered set. Yeah, we can restrict our attention to deterministic stationary policies for that. Okay, so now let's move to the bottom row of the taxonomy. So now we're going to remove the assumption that the scalarization function is linear. I'm going to define a weaker assumption called monotonically increasing scalarization functions, and we'll see what the solution concepts are for all of these cases. And now the distinction between deterministic and stochastic policies is going to become important. So let's start over here. We have a monotonically increasing scalarization function, we know the weights, and we insist on a deterministic policy. Okay, so let's first start by talking about monotonically increasing scalarization function. So here's an example where that might come up. Imagine you're in this mining example that I talked about earlier. You own this mining company, and different choices about where to send your workers will yield different amounts of gold and silver. Let's suppose that for some reason you have only 3 policies to choose from. So one gives you a lot of gold, the other one gives you a lot of silver, and this one gives you a little bit of gold and a little bit of silver. If you decide that you want policy 3, that implies that you're using a nonlinear scalarization function. So we can see that by looking at this plot. So this is again a weight-space plot just like we saw before. So we have one policy is great for gold and terrible for silver, and the other one is great for silver and terrible for gold. And then here's policy 3. And you can clearly see that policy 3 is totally dominating. It doesn't contribute to that undominated upper surface at all. So if I had a linear scalarization function, I would never want to use policy 3. But if you put yourself in a real-world situation as the owner of this mining company, you might find policy 3 attractive. So you might, for example, have clients that care only about gold and clients that care only about silver, and you'd rather come back to the clients with something rather than nothing. Or instead of just selling the gold and silver, maybe you want to make something out of them, and the thing you want to make requires both gold and silver, so you'd rather have a little bit of both rather than a lot of one. Whatever the reason may be, if policy 3 is attractive to you, then you're using a nonlinear scalarization function. So many, many real-world problems can be modeled using linear scalarization functions, but there are also real-world problems that cannot. So in that case, if we're not willing to restrict our attention to linear scalarization functions, we can make a weaker assumption, which is that the scalarization function is monotonically increasing. So formally, we say a scalarization function is strictly monotonically increasing if changing a policy such that its value increases in one or more objectives without decreasing in any other objectives also increases the scalarized value. So what does this mean? It means all else being equal, you'd always rather have more of a certain objective. So if I can change my policies such that I get more of one objective and everything else stays the same, that's a good change. So that's what's written here. So I would argue that this is a minimal assumption, in the sense that I cannot weaken this assumption further without making the notion of an objective very counterintuitive or even just meaningless. So for example, you know, it's sort of in the single objective planning setting, if you're just planning in a Markov decision process, an implicit minimal assumption is that reward is something you'd always rather have more of. Return value is always something you want to have more of. You know, you can easily think of cases where that isn't true, where you say, okay, yeah, I'm collecting gold and silver, but I have to store it in the warehouse, and when the warehouse gets full, I'd actually rather not have the gold. But in those cases, you would argue your reward function hasn't been defined properly. You know, if you don't want to maximize it, it's not a good definition of reward. And this is just the multi-objective analog of that minimal assumption. So if utility isn't something that I want more of, even when all else is held equal, then there's something that's wrong with the definition of my objectives. Okay, so it doesn't have to be linear, it just has to meet this more minimal assumption. Okay, from this minimal assumption follows very naturally the notion of Pareto dominance. So one policy in Pareto dominates another when its value is at least as high in all objectives and strictly higher in at least one objective. So basically, in a pairwise way, we can rule out policies using this notion of Pareto dominance that stems from this notion of the strictly monotonically increasing. If it's true that I'd rather have more of an objective, all else being equal, that means a policy which gets me more of that objective without costing me elsewhere is a preferable policy. So we say a policy is Pareto optimal if there's no policy that Pareto dominates. And obviously we'd like to have the Pareto optimal policies. So our solution concept is going to be built on that. Okay, so here's a slide that answers your question from earlier. So now I have a potentially nonlinear scalarization function, only assuming it's monotonically increasing. So the difficulty that this creates is that it can destroy additivity. So I've got this nonlinear scalarization function. So I'm going to try to apply the trick that I did before. I've got my scalar value here. It's the output of my scalarization function, which takes as input the multi-objective value and the weight parameter. And this here, this first parameter to the scalarization function can be rewritten as this expectation. But I can no longer push the weights inside that expectation. So this is no longer equal to this the way it was in the linear case, because my scalarization function is nonlinear. The scalarization and expectation do not commute. I can't switch the order. So what this means is that any planning method you have which is based on the Bellman equation is not going to be directly applicable. And even if I had some computationally efficient way to find optimal value, I would no longer be able to do this local action selection trick. So this idea that if I just compute the optimal value function, then deciding how to act is easy because I just am greedy with respect to that value function, that will no longer be the case. Right. Okay, so the corner of the taxonomy that we're in is considering monotonically increasing scalarization functions that might not be linear. The weights are known, but we're restricting our attention to deterministic policies. So let's talk about that for a minute.
So, can you please still go back to the previous slide for clarification?
Yeah.
So instead of having the explicit nonlinear function f, you're going to have the Pareto front, and you're going to represent all these points explicitly, your covered set.
Yeah.
And you assume that those will represent somehow an optimal solution relative to this f.
Yeah. 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 So I haven't actually said what the solution concept is yet. I'm getting there, but
yeah.
What you said is exactly right. So just like in the previous case, I had this convex covered set. Now I'm going to have a Pareto covered set, which is the non-linear analog to the convex covered set.
So the Pareto front requires the convexity of the or that earlier convex assumption from before. You assume
No.
It does not.
It's weaker. So the Pareto front in general is going to be bigger. The linear scalarization function is a stronger assumption, and that's going to yield a smaller solution. Makes sense? So now, because I'm not assuming the scalarization function is linear, I have to consider more possible solutions. So the Pareto front will, in general, include things that are not in the convex covered set.
But the optimal solution will be represented by a single policy in the end. So one of them will be optimal with respect to this.
Once I select the weights, yeah.
Yeah, exactly.
Other questions? Okay. Right. Okay. So deterministic versus stochastic policies. So in most settings, stochastic policies are fine. We would raise no objection to them. But there are situations in which they're inappropriate. So if you think back on this medical treatment scenario, if you go to the doctor with an illness and the first thing he says is, I've got a great solution, I've got a great treatment plan for you, the first thing we're going to do is flip a coin. You might not feel comfortable with that. Even if you feel comfortable with it, the doctor may not feel comfortable with it ethically. rolling the dice on your treatment and your life. You personally may or may not think those ethical concerns are valid, but for whatever reason, there are some situations where people would rather not have stochastic policies. So if we, for whatever reason, restrict our attention to deterministic policies, that isn't always a problem. So for example, in our regular single objective Markov decision process, it's not a problem. It's well known, as I mentioned earlier, that there always exists at least one deterministic optimal policy. So restricting our attention to deterministic policies is not going to cost us any value. The same is also true for multi-objective Markov decision processes if we restrict our attention to linear scalarization. So this is probably not surprising because, as I said before, because those operators commute, I can just define, use that weight vector, I can define a new MDP with a scalarized reward function. So it's not surprising that this property carries over. In a multi-objective Markov decision process with nonlinear scalarization, that's no longer true. So stochastic policies may be preferable if they're allowed. So we'll see an example of that soon, maybe very soon, I don't know. And if stochastic policies are forbidden, then non-stationary policies may be preferable. So as I mentioned in response to an earlier question, we can sort of mimic the behavior of a stochastic policy using a non-stationary one. And that could be desirable if the scalarization function is nonlinear. So this is a big complication introduced by the nonlinearity in the scalarization function. Yeah?
Just to go, I think there are also single objective MDPs with different criteria for which there are no deterministic stationary policies. For instance, if you try to minimize the standard deviation instead of
it's not additive, right?
No, not additive.
Yeah. Yeah, so this holds for additive, and this is like your standard MDP.
Standard MDP.
Yeah. If you care about risk minimization, or like there are many other variations on the MDP that might also destroy this property. Yeah. Okay. Right. Okay. So let's look at an example of where we might prefer a stochastic or non-stationary policy. So this is an example that was developed by White. Back in 1982, so White is the guy who did a lot of seminal work on multi-objective planning. Okay, so let's suppose you have an MDP that has only one state, and there are 3 actions available to you in that state, and the multi-objective value of each of those actions is shown there at the top of the slide. Right? So what this means is that there are 3 deterministic stationary policies. So these stationary policies say either always take A1, always take A2, or always take A3. So remember, a stationary policy allows you to condition only on the state. And here there's only one state, so you can't condition on anything. So your only option is to choose one action and then just keep taking that action. Now, the multi-objective value of each of these stationary policies, deterministic stationary policies, is shown here. So this comes from these reward functions, but just now taking the discount factor into account. Okay? But now let's consider a non-stationary policy which alternates between A1 and A2. So because the policy is non-stationary, I can do this. On the even time steps, I can do A1. On the odd time steps, I can do A2. So now I'm going to get this different value here, which is, so it's not quite the same for the 2 objectives because I had to start with 1. So the other one's already going to be a bit discounted by the time I take it for the first time. And then now let's look at what happens in objective space. So each of these plots shows in black the value of the 3 deterministic stationary policies. So this is again objective 1 and objective 2. And in red we see the value of the non-stationary policy. And each of these boxes just differs in terms of gamma, how I set the discount factor. So it turns out that if I set the discount factor to something greater than or equal to 0.5, then this policy will be on the Pareto front. It will not be dominated by the deterministic stationary policies. So you can see that here, so here gamma is 0.7, you can see this is, it's better with respect to both objectives. When it's exactly 0.5, it's better with respect to one objective and the same with respect to the other objective. So just to make the example even more concrete, suppose I say gamma is 0.5, and my nonlinear scalarization function is the product of the two values. And if you work out the numbers, then you see v1 and v2 will be 0, v3 will be 4, and the non-stationary one will be 8. So because my scalarization function is nonlinear, deterministic policies will not suffice. Okay, so that allows us to finally answer the question corresponding to this bottom left box. I've got a monotonically increasing scalarization function. I know the weights, so I only need one policy. But because I'm restricting my attention to deterministic policies, that policy could be non-stationary. The optimal one might be non-stationary. Okay. So now a minor variation on that setting is this one. So we have the same as before, monotonically increasing. We know the weights, but now we're permitting stochastic policies. So now this is just like before. The only difference is I don't need to do this non-stationary thing. Instead, I can do a slightly different trick, which is just to define a mixture policy. So a mixture policy is like a probability distribution over a set of policies. So I have some set of n deterministic policies, and to each one I assign some probability. And then, at the beginning of each episode, I sample from this distribution, and I act according to the selected policy. So the value of this mixture policy is going to be a convex combination of the values of the constituent policies. And so in White's example, I can create a similar policy. Instead of this non-stationary policy, I'm just going to create a mixture policy. And the mixture policy is just going to assign some probability to policy 1, some probability to policy 2. And then I'm going to get this multi-objective value, where the value of each objective is going to depend on the probability that I assign to the corresponding underlying deterministic policies. And, okay, it's not showing here, but just like before, if I make appropriate choices for P1, then I can construct this mixture policy such that it is not dominated by any of the deterministic policies. This is very similar to what we saw before, but now because we have the freedom to choose stochastic policies, it won't need to be non-stationary. But it may need to be stochastic. But we can represent that stochastic policy using this mixture policy of deterministic policies. Okay, so let's move on to the last corner of the taxonomy. So,
quick question.
Yes.
So now let me ask the question that I was confused about.
Okay.
Suppose I allowed myself to store the amount of objective I have gained so far since the start of the process in my state space. Do all the problems go away?
Well,
in other words, can I now do a one deterministic stationary policy in this new augmented state space? And it would be fine.
I guess it depends on whether adding that to the state space is going to make the scalarization function linear, but I don't see why it would.
No, it would not make it linear.
Then I don't see any reason why these problems wouldn't still exist. But I haven't thought about this case, so I could be wrong. Do you want to say something?
Yes, so I have. So indeed, you could add all the reward you have accrued so far to your state space, which might indeed produce a better policy with respect to your nonlinear scalarization function. If you condition on that, typically because you add these returns that you've gained so far to your state space, the problem is going to be untractable because it has too many steps.
So I agree with you. So I'm growing up my state space, I'm making it non-discrete, I'm making it continuous. There are more problems with it. I was just wondering whether some of these problems go away.
But are you saying this would obviate the need for stochastic or non-stationary policies? I don't see
so
that.
my hypothesis, without giving it enough thought, is that one might be able to do a one deterministic stationary policy in that augmented state space. I have to go back and check that.
I think that was indeed the case.
Because the scalarization function is linear, or are you saying that's another special case in which deterministic policy suffices?
I think it's sort of special case.
Yeah, okay. That I would be more inclined to believe. So here we're just saying, in general, it could be the case that you need a stochastic or non-stationary policy. It's not for sure that you need it. So the linear case is one special case where you don't need it. But there can be other special cases, and your suggestion may be one of them.
And the intuition is that anything that has happened so far is all now part of the state space. So why should you now need to make a different decision in the state. I mean, that's sort of the vague intuition. I will.
Yeah.
So I've grown up to put everything in my state now, so I shouldn't need stochasticity anymore. But that I will check.
I think you're probably right about that. That's a good point. Did you want to?
No, I just wanted to say. No, I was agreeing with you.
Okay. Okay, that's very interesting. Other questions or comments? Okay, let's move on to the last corner of the taxonomy. So monotonically increasing scalarization function, but now multiple policies. So unknown weights or decision support. So
Could you explain what you mean by study versus network?
oh, this is an example that I didn't go through. It's just trying to give an example of where this might occur. So suppose you're a student and you have to decide how much time to spend studying a network. So because those two things might interact, the value of one might depend on the other. You know, like at the end of the day, you want a good job, and you know, studying will be useless if you don't do any networking and vice versa. That might make your scalarization function nonlinear. And unlike in the medical example, you probably would not object to stochastic policies in this case, because it's not like a medical, it's not like the ethical complications that come up in the medical example. Okay, so we have these two cases still to consider. Let's start again by restricting our attention to deterministic policies. Okay, so just like before, we had a special case of the undominated set for the linear scalarization function, and that was the convex hull. Now we have the special case of the undominated set for the monotonically increasing scalarization function, and that's the Pareto front. So the Pareto front is just all the Pareto optimal policies. It's a set of all policies that are not Pareto dominated. Okay, and just like before we had the special case of the covered set for the linear case, that was the convex covered set. Now we have the special case of the covered set for the monotonically increasing case, and that's the Pareto covered set. So it's the subset of the Pareto front, such that for every policy, it contains a policy that either dominates it or has equal value. So before, the covered set was covering all the weights, but now, because Pareto dominance is a pairwise notion, we need to cover all the policies. So every policy that could be dominated, we need to dominate it by something in our Pareto coverage set. So let's go back to these visualizations that we saw before. So this is exactly the same example as before. We have two objectives, and we have a bunch of different policies. And as before, this was the convex hull. But now we have this black point, and the Pareto front is going to consist of everything that was on the convex hull plus this point. So this is a point that's on the Pareto front but not on the convex hull. Now why is that? We can see that by looking in weight space. So this black line corresponds to this black point, which is on the Pareto front but not on the convex hull. And we can see that because clearly it's not on the convex hull because it doesn't contribute to this undominated upper surface. But it's on the Pareto front because although it's dominated, there's no single other vector which dominates it. So the Pareto front is everything which is not Pareto dominated, and Pareto dominance is a pairwise notion of dominance. So to rule out a policy, I need to find a single other vector which is always above it. And that isn't the case here. Different vectors need to team up in order to dominate this. And it's that teaming up which is captured in the convex notion and not in the Pareto notion. Okay, so the Pareto front can be bigger, can include these policies that are not pairwise dominated.
It's also true for the blue guy, right?
It's true for all of them.
The blue guy's on the convex hull, but not in the convex coverage set, because he does contribute to the undominated upper surface, but I can represent that surface without him, because he only contributes in points where other policies are also optimal.
Yeah,
But-
but it's still Pareto too.
Yeah.
Yeah, everything in the convex hull. So
Hold on.
this, and this is Pareto optimal. This is the only guy that's Pareto optimal, but not on the convex hull.
Why? Okay, why is? Okay, you said the blue guy is on the convex hull or is not?
It is.
The blue guy is on the convex hull, but not in the convex coverage set.
You can just ignore
Ah, because at
just
one
pick
point
up.
is on the
Yeah.
is on the convex.
This is the only point where he's optimal,
Ah,
others are
okay.
also optimal.
Yeah.
And so everything in the convex hull is also Pareto optimal. But there can be things that are Pareto optimal but not on the convex hull. Yeah?
Good question. So these kinds of diagrams feel very similar to MOMDPs.
Yeah.
We discussed the connection between the two, or can we convert every MOMDP of that box or that corner into a MOMDP or vice versa?
We can convert a multi-objective MDP into a POMDP, where these weights will then correspond to the belief. And we can apply POMDP planning methods, but they are not efficient. So we can apply POMDP planning methods that compute a solution for every belief, which not all POMDP planning methods do. But if they do, we can apply it, but it's not efficient. So there are multi-objective methods that are much better. So White proposed that in 1987.
And what about the inverse? So then QMDP was the objective method, since it's more effective.
I assume that you can't convert MDPs into multi-objective.
Yeah. This is right.
No.
I don't think so. No. No, because, so here's the thing. If I model my multi-objective MDP as a POMDP, it's a POMDP in which the hidden state is something about which I get no observations. I don't know what these weights are, and the whole time I'm planning, I never get those weights. Whereas in general, a POMDP, you have a hidden state that can become more or less known depending on your observations. You can actually update that posterior belief. Here, you'll never update that belief. So I think the reverse is not true.
Yeah, some people call them non-DBs, non-observable.
that would mean you don't see any of the state. Whereas here in MOMDP, there are lots of state features I do observe. It's a mixed observability.
Right.
Some things are I never get any information about, and some things are totally observed. Okay. Right. Okay. So another way that I can see that this guy is Pareto optimal by looking at this box that's up and to the right of him. There's nobody there, so there's no one who dominates him. To dominate him, you have to be in that area. Okay. So what that means is, if my scalarization function is monotonically increasing but not necessarily linear, I don't know the weights and I restrict my attention to deterministic policies. The solution concept I'm interested in is the Pareto covered set of deterministic, potentially non-stationary policies. Again, it could be non-stationary for the same reasons we saw before. So notice, in this whole taxonomy, this is the only box where I use the notion of Pareto optimality. So contrast this with the axiomatic approach that we talked about at the beginning, where we just define as an axiom that the solution concept is the Pareto form. So that doesn't jive very well with this taxonomy, because this taxonomy suggests that actually most of the time you should be using a different solution concept. Okay, so let's go to the last box. How am I doing on time? I need to... Okay, I'll be done in a few minutes. Okay, so the last box. Monotonically increasing scalarization function, but now we allow stochastic policies. Yeah, I think this is actually my last slide. Okay. So this might be another setting in which you would expect that we would need to compute the Pareto from, but it turns out we don't. So if I compute a convex covered set, and I compute that convex covered set considering only deterministic and stationary policies, it turns out I will also have computed a convex covered set for the space of all possible policies. So again, this is not surprising. If everything is linear, then restricting your attention to deterministic stationary policies doesn't cost you any value. Okay, so that will give me a convex covered set, but it won't necessarily give me a Pareto covered set, because the Pareto covered set might require stochastic policies. Remember, we saw this in White's example. However, this Pareto covered set can be constructed by mixing policies on the convex covered set. So I can compute this convex covered set for deterministic stationary policies, and then anything that you think I might be missing, like you say, hey, look at this point here, it's Pareto optimal, so it's not in your convex covered set, so you missed it. But if I'm allowed stochastic policies, I can take anything in my convex covered set of deterministic policies and mix it. And by mixing it, I can get any value on this line. And you can see part of this line is in this region that dominates this Pareto optimal point. So this point cannot be Pareto optimal, so I don't need it. So even in the case where at the end of the day I do want a Pareto covered set, if I allow stochastic policies, I don't need to actually compute that Pareto covered set. I can just compute this convex covered set, restricting my attention to deterministic stationary policies, and then mix them however I like in order to get undominated value. So this last box, the solution concept is a convex covered set of deterministic stationary policies, which I then mix however I like. So as a result, this becomes the only box that requires the Pareto. So that concludes part 1 of the tutorial. I think now it's time for a coffee break. After the break, Diederik will tell you all about methods and applications for these problems that we just did. See you guys in half an hour.
Okay, ladies and gentlemen, welcome back. My name is Diederik. I'm a postdoc at the University of Oxford here in Shimon. And in the second part, I'll be covering different methods for multi-objective decision making. The first part will be about multi-objective decision making in the context of multi-objective MDPs. And then I will talk about multi-objective partially observable MDPs, which you might already have some familiarity with. And finally, I will show you some, I think, rather cool applications of this field. So before the break, we saw this schema quite a lot, and I'm going to talk about all the boxes that are indicated in red here. So I will not focus on monotonically increasing single policy methods anymore. So first, I should point out that there is a difference here between the planning setting, which I'm going to focus on. So we have known transition and reward functions. And we're just going to use this complete model in order to make a plan and then execute it. The converse of which is the learning setting, in which we do not know the transition and reward functions, but I will not be focusing on this during this tutorial. So first, let me start with some background. I'm sure you're quite familiar with this, but just to be sure. I'm going to start with an algorithmic value iteration, which is based on this Bellman backup, which we solved before the break. It's an algorithm to compute the optimal value function and by doing so also compute the optimal policy for a single objective MDP. So starting from some initial value estimate for every state, we apply what they call Bellman backups until this converges. So from our current value, we say, okay, what would be the optimal action to do in a given state? Marginalize over the transition function, sum the immediate reward, and then the discounted value of the state we end up with. And we keep on doing this until it converges, and then we have the optimal value function, from which you can also extract the optimal policy. But in order to do so, it's more convenient to write it like this. That is, we maximize over certain Q values, and we keep these Q tables, which is the value of a state and an action, and then following the optimal policy. And this is nice because we can quickly retrieve the optimal policy. Okay. So first, let me begin with the top left corner of the taxonomy, which is single policy and a linear scalarization function. So this was the simple case. Namely, if we have a known scalarization weight that's linear, it nicely distributes over this expected sum of rewards. And so the easy thing to do is to just scalarize the reward function of the MOMDP, leading to a single objective MDP, and apply standard value iteration, which we just saw. However, you might also want to retain the multi-objective value of your policy, and if you scalarize a priori, you won't get that immediately. So we can also make a slight adaptation in order to retain this multi-objective value, just to inform the user of the system. And we could do it like this. We could keep a value vector Q table, and then use maximization, but then keep these vectors as vectors. And if we do this, then this will be the exact same algorithm, but now it will also return the multi-objective value of the policy that we computed. All right. The nice thing about that is that I'm going to use these policy values later in the later algorithm. So now let's move to the second box, or actually two boxes. The cases in which we need the convex covered set of deterministic stationary policies. There are two ways in multi-objective, or two standard ways I must say, in multi-objective decision making to create a multi-objective planning method from a single objective planning method. So we take, for example, this value iteration method, and we build on that in order to create a multi-objective planning method. There are two ways to do this. The first one is called the inner loop method, in which we take the single objective method and then we take these maximization and summation operators inside this single objective method and we replace them by operators that can work on sets of value vectors. So this will typically be cross-sum operators, cross-sums between two sets, and then pruning away vectors that we don't need. So in order to do this, we need to make a series of multi-objective operations. For example, we make multi-objective operations, multi-objective versions of this belt and backwards. The other way is to take a single objective method, but then embed it in an outer loop, which deals with these multiple objectives, and then this outer loop can call the single objective method or a scalarized method that returns the multi-objective value repeatedly in order to iteratively build the coverage set. So an output method uses a single objective method as a subroutine and solves a series of scalarized or single objective problems. Right. So the first method I'm going to discuss is an inner loop method called Convex Hull value iteration. It was proposed by Barrett and Narayanan in 2008. And the key idea behind this algorithm is to do the Bellman backups, but now not the single objective Bellman backup, but the Bellman backup for all possible linear scalarization weights in parallel. So this new backup operator must be able to deal with sets of value vectors, because in the end we also need a set of value vectors to return. So this, namely the Convex Covered Set. So in each backup, we're now going to generate all possible value vectors for each state action pair, and then prune away those vectors that are not optimal for any linear scalarization. And as Shimon mentioned before, because we're in the Convex Covered Set setting, we only need deterministic stationary policies. So that's fine. All right. So how do we go about this? Well, we start from an initial set of value vectors. For example, the single set containing the, in a two objective example, just the vector 0, 0. Then for all possible value vectors, we need to compute these backups. But now we have a multi-objective, so a vector valued immediate reward, and we have a set of possible next state values, which are also there. Okay, so the first thing we do, we need to be able to sum this up. So we can do this by taking this immediate reward in this set and just translating every vector in the set by the immediate reward. Then, to marginalize over the next state, we need to take cross sums over all possible sets that are in this, that are the result of this. So cross sum is just taking every possible combination from two sets and then summing them up and then putting them in each set. So you can see that this might be quite an expensive operation, right? Depending on the size of these sets, it's going to be really big. All right. So now we've generated all possible values by a one-step loop ahead. And then what we need to do is we need to prune away those value vectors that we know are not optimal and we cannot use in order to get optimal values in the future. And we can do this by doing a pruning operator. For example, here we refer to this as cprune, which uses linear programs in order to get rid of those vectors that are not optimal for any weight. And because this linear scalarization weight distributes over this sum, we know that if we then later add some more reward to it, then still a dominated vector there cannot contribute.
How large are these linear problems?
That's a good question. So there are at least a number of columns that are equal to the number of objectives, plus the number of rows that are maximally the size of your intermediate sets. However, you can do some pre-computing there so that you can limit the size of these intermediate sets a bit. So for the details of that, I can show you in the break.
Okay, great. Thanks.
Excuse me. I think I missed the reason for the question, because it means that we mix values of different weights.
Yes. So this cross sum is here to marginalize over the possible next states. So for each possible next state, we have a different set of value vectors.
Right, but why cross sum? I mean, it means that I take a value, an objective value for this prime, then I mix it with another, with a different objective.
Different objective. No. No, I'm mixing sets of value vectors. So from each of these sets, I pick a complete vector that has a value in each objective, and I only combine them across different subsequent states. So it's not mixing different objectives. Does that answer your question?
Yeah.
I will show you a numerical example in a minute, but I think it's clear. So numerical example. So if we start with a very simple MOMDP, with just a single state, two actions that recur back to the state, actions A1 and action A2, and deterministic rewards, taking action A1 always leads to 0, and taking action A2 always leads to 0, 2. And we are going to use a discount vector of 0.5. Furthermore, we needed an initial guess for our sets of value vectors in every state. So we only have one state, and we take a singleton set of the vector 0, 0. So 0 in objective 1, 0 in objective 2. Okay, now what if we apply our multi-objective Bellman operator? Starting from our singleton set, we can now compute these Q values very simply, because taking action A1 results in 2, 0, and then the value of the next state, we have only one possible option here, that's the 0, 0 vector. And the same for action A2. So now we plot these and we apply this pruning operator. So first we merge these two sets, and then we look whether we can prune anything from this set. And it turns out we can't, because both vectors are. So next iteration, we now start with the set of value vectors here with these two vectors that we got from the previous iteration. Then if we add our immediate reward and then take the discounted value of the next state, then we get 3, 0, so that is 2, 0 plus, and then gamma times 2, 0. And we take 2, 0 plus gamma times 0, 2. Does that answer your question?
Yeah, it's exactly the same thing as the person in MOMDPs with observations. So, I understand it. As the person in POMDP, I think.
Yeah, I don't know. Okay, so now if we take the union of these two, then we get these four vectors. And now when we apply C-prune, then we know that we can remove some, namely these two dashed lines, because they're only optimal in one point and we only want a convex covered set. So we can get rid of these. And then we turn up with 3, 0 and 0, 3. So, next iteration, we do the same thing, obtain the following Q values, take the union again we get 4 different possible values, we C-prune again, and the dashed ones go. So, because C-prune now retains at least one optimal vector for every possible W, we know that if we would apply a scalarized version instead, then this same policy would have been retained, or at least an optimal policy would have been retained. So this exactly does the backups for all possible linear scalarization rates in parallel. Furthermore, we know that CHVI does not retain excess values because we're doing this exact C-prune thing. So all values that are not useful are being pruned. However, it might not retain them, but it does generate vectors that we don't need, right? So we have these dashed lines in the example that need to be pruned. And the more of this we have, the more expensive the method becomes.
Is there an easy way to check whether you need to run C-prune or not?
Whether you need to run it at all. So no, there's no easy way to quickly check whether all vectors that you currently have are optimal. So that's no. You can, however, use a simpler type of pruning first, but that's that retains too many vectors, and then you have a smaller linear program. All right. So contrary to this inner loop method, we can also use a different approach, namely this outer loop method, which is the outer shell around the single objective solver. And this is a very generic multi-objective method because we don't need to touch the inner workings of this single objective method, unless perhaps to make it return a multi-objective value instead of a single objective. But it's not a big works on the single objective method. And that is why this applies to, for example, also not only MOMDPs, but also multi-objective coordination problems, multi-objective multi-agent MDPs, or multi-objective partially observable MDPs. So how does this work? So this is actually our own method, which we call optimistic linear support, and it adapts and improves upon the linear support method for MOMDPs proposed by Cheng in 1988. And this solves scalarized instances for specific linear scalarization rates. However, by picking these linear scalarization rates in a clever way, we can guarantee that this terminates after checking only a finite number of these linear scalarization weights and returns an exact Convex Covered Set.
Sorry, what do you mean by linear support exactly?
I will show you in a minute. Okay. So, how linear support works? Simply, we're going to pick linear scalarization weights in order to obtain multi-objective values for given weights. And we know that these are optimal for at least one weight because we've solved them at least one weight. So we start at the extrema in a two-objective problem, just 0 and 1. And we find these two value vectors. So in order to now pick the next weight, because the extrema is to pick, we should then figure out where should we search again. And it turns out if we look at the exact border between where these two values are optimal, namely these so-called corner weights, then if we search there, then we can in fact gain an optimal CCS. Because the maximum possible error that is attainable, that we might still have, is also at one of these corner weights. This is a mathematical result from check. And it's called linear support because this region is called the current support region for this vector. So this is where this is optimal. Okay, so if we look at this corner weight, we find a new vector, then we get two new corner weights. And if we look at them both and then do not find a new vector, because of Cheng's theorem that the maximal possible improvement on the intermediate CCS is on one of these corner weights, we know that if we don't find an improvement, then naturally the maximum improvement is 0 and we are done. Okay, so this works reasonably well. However, we made an improvement to this, and that is if we know this maximal possible improvement, that is, if we've observed that the optimal value for 1 is this one, for 0 is that one, then we also know what could be the most optimistic vector that we could still find that is consistent with our current observations, which is this dashed line above here. So we could still find a vector that looks like that. So the maximum possible improvement is in fact this delta. And if we retain this and then prioritize corner weights with respect to this maximum possible improvement, this gives us some nice properties. First of all, by prioritizing this, we know that we are always going to maximally decrease the error, and we're going to know the maximum possible improvement at each step in our algorithm. So this gives us the result that while we're running, we know how much error there's maximally left. And this also gives us the opportunity to stop early. For example, we only need an epsilon optimal solution set, then we can stop when delta becomes smaller. And of course, for very small MOMDPs, as here shown in the tutorial, this is you might not want to stop beforehand. But if you have a very large problem, then you might want to do that.
So I can interpret this as the optimality gap in this case.
Yes. Yes. Another nice thing about this is that this is very useful when you cannot, in fact, compute the optimal value, but can compute only an epsilon approximate single objective value. So for a lot of planning problems, computing the optimal solution is too expensive, but you can get a lower bound on this value and guarantee that it's only epsilon better. And this transfers directly to this optimistic linear support, because all that will do is transfer this optimistic CCS, the dashed line, epsilon up. And so we can still compute the maximum possible improvement. Of course, then this will no longer convert to an optimal CCS, but it will convert to an epsilon optimal CCS. Okay, so if we now compare the inner loop method to the outer loop method, the outer loop method has these advantages over the inner loop method. First of all, it can apply to any multi-objective problem without much tweaking. Furthermore, it can apply any single objective or scalarized method as a subroutine, so we can quickly select any and replace single objective methods. And it inherits the quality guarantees from these single objective methods. So it's an epsilon approximate single objective solver. We can have an epsilon approximate CCS. And it's faster than the inner loop method for small and medium numbers of objectives. However, if you have a vast number of objectives, then the inner loop methods are actually faster. So it depends a bit on your problem which one is faster in practice. All right, are there any questions so far?
Yeah.
Yes.
It looks to me that the algorithms are exactly the same as the witness and incremental pruning algorithms for MOPOMDPs.
So it's inspired on the MOMDP method, namely chain linear support method.
Yeah, it looks more than inspired. It seems that it's the same, but perhaps I'm wrong. My question is,
well, there are some key differences. Namely, first of all, we do actually compute this maximum possible improvement in order to prioritize between corner weights, and Chain just computes for every possible corner weight. And this is because Chain does a full backup in a MOPOMDP, generates a lot of vectors, and then finding a new vector is maximizing over this list. However, finding a new vector here is solving an entire single objective MDP. So that's a much more expensive operation, and therefore it's way more important that you prioritize these corner weights accordingly.
actually, my question was, if people try to generalize point-based MOMDP methods to multi-objective MDP planning? Do you know what
Yes, yes. I know actually we have a point-based method for multi-objective MOMDPs, which will be later in the tutorial. So the problem with point-based methods is that you don't have these nice optimality guarantees. Right? So yeah, but you could randomly sample different weights. However, the key feature of a point-based method is that you sample these weights in a more intelligent way. Namely, you do it by execution and then finding different belief points. However, because you get no observations about your weights whatsoever, that's not easy. So then you're basically stuck with random sampling, which is not preferable.
Random sampling is a baseline which OLS outperforms in multiple experiments.
And so the other thing is comparing to check method is just the matter of applicability. So while you have multi-objective, when comparing MOMDPs to multi-objective MDPs, the number of states in the MOMDP corresponds to the number of objectives in the multi-objective MDP. And while MOMDPs typically have a very large number of states, the number of objectives in a MOMDP are typically limited. Especially here, the inner loop method is faster for large numbers of objectives. So if you have only a two-objective problem, this is going to be faster, but when your number of objectives grows very quickly, or in a MOMDP the number of states, then this is no longer very effective. So there's a key difference there between multi-objective problems and observable problems, is that what is important for scalability is different. So the importance, so what features of the problem make it scalable are different. So the number of objectives is typically limited, whilst the number of states in the MOMDP is a key feature of scalability. Did you answer? Yeah. Okay. Any other questions? Alright. Then let me continue with Pareto Covered Set method, also based on value iteration. Maybe just Pareto Q, which is very similar to CHPI, except we are now using a different pruning operator to get rid of the vectors that are dominated. So we're only going to do pairwise comparisons now. And as you might already notice, these pairwise comparisons might be a lot cheaper than these linear programs we've done before. You might think that this might be faster, but in fact it isn't, because there are going to be way more vectors in these intermediate sets. And actually the size of these sets is what's going to make it expensive. So the advantage here is that it does converge to the correct Pareto Covered Set, but there might be a lot of vectors involved and it might be slow. Furthermore, executing a policy is no longer as trivial as for linear scalarization weights, because if you get a linear scalarization weight in your known weight scenario, for example, you can just pick one of the values that corresponds to these weights, and then you can find the optimal actions from your Q table with your weight. However, for Pareto Covered Set with nonlinear functions, this is no longer trivial. Alright. Pareto Q, very quickly, it does the same types of backups to compute these Q tables. That takes again the union across the different actions and then pruning away the Pareto dominated vectors. And so this is also the simpler pruning method that I mentioned that can make your linear program smaller if you do this Pareto pruning first and then do the linear program. Alright, so what happens in practice? So I'm now going to use not this weight space as you've seen before, but now I'm going to use objective space to show the intermediate results. Okay, so again we start from the vector 0, 0. And then in the first iteration we are going to get identical results. So we get two possible Q values, take a union, and we can't prune anything. So I'm going to use red to indicate what happened in CHVI instead. However, in the next iteration, we can generate these two Q tables, but contrary to the linear case, we can now no longer prune this vector and this vector. So we're going to have to retain. And so here we get the two black points, whilst in the linear case we would only have the red points. Okay, next iteration. We're going to get quite a bit more vectors, and I think you see where this is going. This is going to happen ad infinitum and just create a lot of points along a line. And so this is also why this method can be very expensive. Okay, so the size of this Pareto covered set can explode. Furthermore, it's no longer the case that we have deterministic policies. Because these Bellman backups might actually, they do rely on being able to take an action A in a state first and then take another action in the same state when we encounter them again. And this is implicit in these Bellman backups. This also means that we can no longer just read the optimal policy from the Q table, right? Because this Q table are only a one-step look ahead, so if we read a Q table, we would always take the same action, which is obviously not the case. So for all these policies, we need to take different actions in the same step. So except for the first action, we can read the first action, right? So what do we do then? Well, if we can track a policy during policy execution, so for deterministic transitions, this is quite still rather easy. So if you have a deterministic transition, it means that if we take a state action in a certain state, we always transition to a specific state, right? If we have deterministic transitions, then we can subtract the immediate reward we just got from the Q function, and also, by the way, deterministic rewards. Subtract it from the Q function, correct for the discount factor, then the value that we're supposed to get in the next iteration, and then find that again in the Q tables. So this is a bit more involved. But this also relies on having both deterministic transitions and deterministic rewards. If instead you get stochastic transitions and stochastic rewards, it becomes a lot more involved. It's actually quite an algorithm, which I will not show here, but you can find it in the PhD dissertation by Christophe van Moffat. Okay. So what do we do? So we've now seen an inner loop method for computing in PCS. However, we might also have a look at what we can do with an outer loop method. And this is also going to be difficult because, as we've seen before, the scalarization function cannot be pushed into the sum. So if we do this scalarization trick, then there is no guarantee that just maximizing over these scalarized values in between will give us the optimal policy, or the optimal value. Doesn't mean that people haven't tried, but it becomes a complete heuristic. So, and also in this paper, it shows that sometimes it does find a reasonable some of the optimal policies in the PCS, but not all, and sometimes it doesn't converge at all. So that's rather difficult. So it's not guaranteed to find an optimal policy or even converge. So this is, so I would actually advise not to use outer loop methods if you want to get PCS. Okay. The next bit I will be talking about multi-objective, partially observable MDPs. So I have two questions. First, do you have any other questions? And secondly, I would like to see some hands. Who of you are familiar with partially observable MDPs?
A little rusty, but
Have you seen them before?
yeah.
Okay. So I will very briefly go over them, but I will not go into detail. So if you are not familiar with MOMDPs, then some of these details might not be that interesting, but there are still several points that apply across different multi-objective problems. I will try to mention them explicitly. If those get lost, please just poke me wait a minute. Okay, so let's take a short break and we will resume in 10 minutes. Okay, welcome back. So the next part I'm going to talk about is the combination of multiple objectives and partially observed policies. And to make that very concrete, I'm going to help this guy. And this is a Mars robot. It's not ours. And this robot has a certain field of where it can perceive things. So it gets observations from the environment, but it cannot perceive everything. For example, it's not observing currently that it's about to run into this rock. And the problem this robot faces is that it wants to cover as large an area as possible to survey the planet while minimizing damage to itself. So there might be some very interesting regions, but getting there might incur damage. So we do not know how to a priori scalarize it. Okay, so what does this do to the problem? Well, we now have our robot, which takes an action. This changes the state of the environment, but in addition to the reward, we are now also getting an observation that does not disambiguate the state of the environment, but might give us information. Alright, so this is a partially observable MDP, in which the state actions, transitions, and rewards are the same as in an MDP, as you know. But then there's also a set of possible observations and an observation function that gives us, given an action we take and a state we transition into, what is the probability of each observation. And this partially observable MDP is equivalent to a belief MDP. That is to say, instead of the state, we now are going to use a belief over which states we are in. And so the state in the belief MDP is a belief simplex over the states of the MOMDP. So this is a continuous state with dimensionality, the number of states in the MOMDP. The actions are the same as in MOMDP, and we now get a transition function which we base on computing this belief and then computing updates for these beliefs for the current belief, the action computing the observation we get, and that will give us the next belief. So this is the belief update, and from this we can extract the transition function between these belief states. And of course we get the reward function, which is now just marginalizing out the state over from the belief with the original reward. So this gives us an MDP, but this MDP is continuous in state. Okay, so obviously when we go to the multi-objective setting, we're going to get vector valued rewards, and this gives us some extra problems. Because both the state-based reward in the original MOMDP and the belief-based reward are now going to be vectors rather than scalars. So the first challenge is how can we represent the multi-objective value? Secondly, single-objective MOMDP planning is already very expensive. So we need to do something to make this more, to make it more tractable. So I'm going to try and take on these challenges in the following way. First, I'm going to start from point-based planning method for MOMDPs, and then building on that, I'm going to first inspect what value representation we need for multi-objective MOMDPs, then go to scalarize point-based planning, so a point-based method that gives us the multi-objective value given a linear scalarization weight. Then and we move to point-based CCS planning, so combining that with OLS. And then finally, I'm going to apply a new trick, which is called alpha reuse, in order to make the outer loop method faster. So this is how we're going to tackle it. So, first of all, value functions for MOMDPs are, especially in point-based methods, typically represented by these alpha vectors. So it's a value for every possible state. And then the value for a belief is then the inner product between the belief over states and this alpha vector, which gives us a value for every state. Okay. Furthermore, we have the point-based method, which is just sampling a set of beliefs, and we are maintaining a set of alpha vectors that are the representation of our value. Then repeatedly pick a belief from this set of sample beliefs and perform a point-based backup, that is a balanced backup for exactly one belief point. And of course, this is not exhaustive because we can't iterate over all possible beliefs because it's continuous state. And we do this until this set of alpha vectors converges. Okay. So the key operator inside point-based methods is the direct projection. So starting from the backup here, we are going to find a new alpha vector that is optimal for this given belief. We compute it by taking the reward factor and then the discounted value of the next state, which we call a back projected vector, which is computed like this for every possible alpha vector that we have in our current set of alpha vectors. So it's the same basic operation scheme as an MDP, but it just looks more complex because of the partial observability. Alright, so the bottleneck here is one of the bottlenecks here is the number of back projected vectors, because each iteration here is going to be linear in this size of the number of alpha vectors we have, and the number of alpha vectors we need might be very, very large indeed. So this gives us problems when we go to the multi-objective setting. Of course, if we know the way, we just go to a scalarized version. But first, if we need the CCS, then if we would apply this inner loop method, where we would use sets of possible value vectors and then going to take the inner product of these cross sums of these from a set that is already huge, then that's probably going to make it interactable. And people have tried this, and it is indeed very bad. Okay. So it's more efficient here to take an out-loop approach and use the scalarized point-based planner as a subroutine. So how do we go about this? Well, first of all, instead of alpha vectors that have a value for every possible state, scalar value for every possible state, we now need an alpha matrix that for every possible state has a vector value. Repeatedly pick a belief point and now back up for both the given belief point and the given W that we have at this time. And then until it converges. So from the alpha vectors we had for single objective methods, we now go to an alpha matrix. So for every state, a value for objective 1 and objective 2, as many objectives as we have. And now the multi-objective value for a given belief is this belief vector times this matrix, which will then give us a vector. So the scalarized version, we are going to use some adaptive point-based backups. So this is the single objective point-based backup, and this is the multi-objective point-based backup. So it looks almost identical, except that we now also have this given linear scalarization weight, and we just add it here. But we have to maintain these alpha matrices instead of alpha vectors. Otherwise, it looks very similar. Oh, this is also a matrix. So, taking this scalarized version of the point-based method. And the scalarized point-based method is just plugging this multi-objective point-based update into any possible point-based single-objective planner. For example, we used multi-objective Perseus here. And now we are going to select, again, following our optimistic linear support scheme, a series of linear scalarization weights based on the maximal possible improvement. Use this scalarized point-based planner as a subroutine, which returns the multi-objective value because we do retain these alpha matrices. But if we just do this, then this would still require us to do an entire run of an entire point-based planner for every scalarization weight that we pick in the series. And that can be really bad. So the size of a CCS can, for example, be 300 points, 300 vectors. Do you really want to multiply your runtime of your point-based planner by 300? Probably not, right? So we're going to use an additional trick here, and that is, if we start from scratch, it's inefficient. However, what we do know is that if, because we have this nice piecewise linear and convex function as a function of our scalarization weights, we also know that if we get weights that are close, then probably these values are also going to be close together. For example, if we have this scalarization weight and this one, then these two lines look pretty similar. Okay, so what now if we would take the alpha matrices from previous calls to hot start our scalarized point-based planner? So if we take the alpha matrices from this vector and then start to compute this vector, then that will give us a big head start. And our hypothesis is that this becomes more and more effective as these weights lay closer and closer together. And of course they will, because the further we go along in this series, the closer these scalarization weights are going to lay together in weight space. Okay, so there are some theoretical results that I'm not going to support by any proofs in this talk, but they are in the paper if you're interested. So first of all, OLS with this alpha reuse trick requires a finite number of calls to the point-based solver to converge. This is just direct transfer from the results we already had for OLS, right? Furthermore, we can produce an epsilon approximate solution set where the epsilon is inherited from the single objective method. So we can, for example, use the density-based approximation results by Pinot et al.
Can you say something about the convergence speed?
Yes, I can. Okay. So, as I've mentioned before, you could instead of OLS, you could also do random sampling of your scalarization weights, right? This is what came up in before question. And if we do that, then this might not be very efficient because we might be solving scalarized problems that we don't need a new value for. So this converges very, very slowly. So by the way, this is the runtime of the algorithm, and this is the residual error with respect to a reference set that we pre-computed using way more runtime. Okay, so just random sampling and then scalarized scalarized planning converge very slowly. Then if we introduce this alpha reuse, but now with this random sampling, then this still converges very slowly. And it might seem like a small improvement, but do know the log scale on the y-axis, right? So what happens if we start to use OLS? Well, first of all, this converges a lot faster than our method, but still not as fast as I would like, because if we add this alpha reuse trick, then you see that we really go orders of magnitude down very quickly. Also note that in the beginning it does not matter all that much, and this is simply because in the beginning these weights are laid very far apart, so we do not have alpha matrices yet that correspond well to new weights. Another thing that I should mention is that if we do not need a new policy for a corner weight, and this is exactly when our method will start to converge, right? So if we pick a corner weight and we do not find a new value, then we will be done very, very quickly, because we only have to check every belief point in our sample belief set once. And we'll just check that the value is still the same. And suddenly my computer does that. No. Yes. It's back. Okay. So what we've done with optimistic linear support with alpha reuse is we've enabled the use of point-based methods for multi-objective MOMDPs. This was the first method, at least to our knowledge, that reasonably scales. We can get a bounded approximation of the CCS, and this alpha reuse is really key to keeping this multi-objective MOMDPs term. Okay. Furthermore, this reuse idea is of course also applicable to multi-objective MDPs, where you can just reuse the entire Q table. However, we did not run those experiments yet, so we will do it soon. Okay, are there any questions? Yes?
Is it at all possible to analyze the convergence speed in a theoretical way, so to say, or is it too hard?
Conversion speed. So the conversion speed of the scalarized method is, of course, the same as the original single objective method. It uses more operation, but its matrices advantage. Furthermore, so then it depends on the number of vectors that you're going to find in the CCS. So we have made analyses based on the number of vectors in the CCS that you're going to produce, but it's not possible to a priori predict how many vectors will be in the CCS. Okay. So that's where it breaks down a bit, but you can get results in terms of the numbers of vectors in the CCS.
As we discussed before, in the worst case, that would actually be all the vectors.
All possible policies.
Yeah, then less we do that. As a function of the size of the CCS, then that's
Right.
In practice, it's a lot smaller.
Yeah, I would make a dumb question then. In practice, how big is this size in the end? I would suppose that the very worst case, well, it's too hard and doesn't appear, so it's not relevant.
Yeah, that's
so yeah, it's hard to tell because it really depends on the type of problem that you're solving. So even between different multi-objective MOMDPs, the size of the CCS might be very different. What is typically true though is that the size of the CCS is more or less exponential in the number of objectives. Okay. So it's not very close.
But yeah, so as we were saying before, scalability in the number of objectives is typically not that important. Most problems have only a few objectives you want to scale out of states.
So the good thing is that the complexity results for 2 objectives and 3 objectives are linear in the size of the CCS.
Okay.
But then afterwards it's going to be inverse.
And what we also see empirically, there are a lot of results to this effect in some of our papers, is that the CCS grows a lot more slowly than the BCS.
Definitely.
And that's why computing only a convex covered set when your setting permits that is key to computational efficiency.
Okay.
So that is actually whenever stochasticity is allowed.
Right.
Actually, I'll ask at the end, because let's finish
Okay.
with the MDP stuff. That question.
The MOPOMDP stuff is done.
Okay.
So I will now.
Yes, I was wondering, so in AI planning, we have very, very, very large MDPs. And so for that reason, we tend to really try to use methods to solve them that are, and also another thing, often they are more stochastic shorter sparse problems than MDPs. I mean, we do both, but, planning people like to have goals, so this corresponds more to a stochastic shorter sparse problem than an MDP. And so some of the methods, for instance, they're called heuristic search methods, things like MOMDP or LAO star, which are trying to incremented, well, they don't start with the whole state space. They start from the initial state, and then they're on the fly, they're basically computing regions that look like they're promising.
Yes.
Do you, I mean, with the type of methods that are just calling the, we call them outer
Loops, yeah.
Could you do something with these this type of methods?
Definitely.
Or?
Depends. So you could always use an outer loop method, and I'm guessing that the values that you're getting with these methods are lower bounds, right? On the actual.
No, you're getting the optimal.
You're getting
The only
optimal.
thing that they're not going to give you some values for things that are outside the optimal policy, right? So they're not reachable for the outside.
Yeah. So I think this is a very interesting line of research, especially because the ones you've already got values for, you can probably reuse. So then you can do this reuse trick, and then you just have to add new information for the parts that you haven't. I mean, I haven't done it, so. But,
I was just wondering
it's very,
whether
possible.
people had tried to use these kind of methods in,
Okay. Yeah. So Allstar was published last year,
Yeah. Okay.
and OLS the year before that. So
Yeah.
probably. Yeah.
The only complication I can think of is if you're talking about online planning methods that are anytime methods, where you plan starting from the current state and you just plan as much as you can until your budget runs out. Then I would say it's not trivial to combine this with an outer loop method, because you have to make some decisions about how to spend that fixed computational budget on each of the calls to the single objective subroutine.
No, I was talking about something offline. But the only thing is, it's offline, but you have to, I don't know.
Just think about a stochastic game, right? So you have an initial state, and depending on the policy you're applying, you can already prune part of your state space because you know never going to happen, right? So
Yeah, sure.
So I guess
Yeah, if it's
that's what
offline-
you're trying to say.
If it's offline, then the only requirement is that you can return the multi-objective value, like before scalarization. But I think for this kind of algorithm, it's a trivial change in the bookkeeping of each node instead of retaining a scalar value in a vector. I think that would be very easy.
But what I'm also wondering about is, it would be a bit too bad if what we would have to do is, run a heuristic search method to find a complete, an optimal policy, even if it's not covering all the states, and then, call it again and call it again. Maybe another, I'm just wondering whether the kind of method you have can also be incremental in themselves. Like, you start from the initial state. Well, if you don't know heuristic search method, it's going to be hard to explain. You start from, you see, these heuristic search methods, what they do is that they only, at some point, they've only explored a part of the state space. They have the best optimal policy found so far. And the fringe of this policy, the states, the fringe of this policy, have heuristic values, so there are lower bounds on the expected cost to reach the goal from there.
And best first.
And it's, you can see it like a best first search. And basically what you do is that you expand those fringe states, generating their successors, and you do this again. And the question is whether you can, whether you can incorporate this kind of stuff in, in your methods, or...
I think, well, it's not trivial, but I think it's definitely possible. But
interesting.
I would love to discuss.
Okay.
So I think if the heuristic you're using is admissible, you can use that to compute epsilon, and then you have an epsilon optimal single objective solver, which you can use in the variant of optimistic linear support, which relies on epsilon optimal solve. So if you want to say you don't want to solve a whole bunch of single objective problems completely, you solve them only partially, you get some epsilon, and then you just take the epsilon into account when OLS is deciding which weights.
Yeah. Okay. So if there are no further questions, I will move to some nice applications of multi-objective decision making that have been published over the recent years. One of the things I like a lot is, well, it's a bit more sophisticated than the image suggested. It's from 2010 and 12. Dan Liesel has been working on treatment planning for medical applications. They try to maximize the effectiveness of the treatment while minimizing the severity of the side effects. And in order to do this, they use finite horizon multi-objective MDPs and deterministic policies. So the deterministic policies, because doctors want that. Okay. Another cool application, I think, is the anthrax response control. If there is an incident with powder, then the CDC might take all kinds of different actions. And their goals in that is to minimize the loss of life, but also to minimize the number of false alarms. So if you get an alarm for anthrax, then the entire area is quarantined, and it's very inconvenient for the people involved. And of course, they try to minimize the cost of investigation because they have a very limited budget. So the first thing here is that it's actually a partially observable problem because you don't know the true state of what was in the powder, but you will get some observations either by symptoms of the people involved or by explicit testing. And the way Undominated solve this is by using finite state controllers for multi-objective MOMDPs, so we haven't discussed this. And they use an evolutionary method to optimize these finite state controllers. And they focus on finding a Pareto covered set. Furthermore, also Undominated have done semi-autonomous control for wheelchairs, where they try to maximize the safety but also the speed and minimize power consumption. And again, they use these finite state controllers, evolutionary methods. It's actually the same paper, but it's two rather cool applications. And finally, what I should definitely also mention is a paper by Dan Bryce, who says that if you're doing probabilistic planning, it's actually always multi-objective. Why does he say it? Well, he says that the expected return is just not enough because you always have some cost of executing your plan. You have the probability of success of the plan, and you have different non-goal terminal states which might or might not be bad, but it's very hard to determine a priori how you should weight this. And just assigning some numbers to each of these are going implies this a priori scalarization, but it's very hard for humans to decide this in advance, and it's way easier for humans to make an informed decision based on actual alternatives, and also it leads to better results. So it's not this paper, but there are also psychological tests which suggest that if you do this a priori scalarization thing, and you investigate it for a long time, and then you produce the actual alternatives, and then you let them big, and then this scalarization function that is specified beforehand is actually going to give you a completely different result than the policy they picked from the actual alternatives. So that indicates that it's very hard to do this a priori scalarization. Actually, while here at ICAPS, a good question to ask for almost every paper is actually, why is this not multi-objective? Alright, so to come to the conclusion, if you're working on planning problems, please do consider using multiple objectives, because most problems have them, and a priori scalarization can be arbitrarily bound. Furthermore, we urge you to derive the solution set from everything you know about the scalarization function. Because if you do not make the assumption and just assume the Pareto front, you're often doing way more work than you actually need. So if you derive your solution set, you can probably narrow down your solution space quite a bit into much more efficient algorithms. And finally, there are a lot of promising applications in both planning and scheduling. that would require multiple objectives. So thank you very much for your attention. So this is the end of our tutorial. Any final questions? Yes?
Do you know in real applications, do we need multiple objectives or one objective and constraints? Or multiple objectives and many constraints?
Yes, it depends. It's often way more natural to express things as multi-objective. So simply...
Yeah, this is the example with the wheelchair, for instance. We try to maximize safety, perhaps should be a constraint also. Safety.
Minimum safety.
Sorry?
So a minimum level of safety.
Yeah.
Yeah, so that
I don't want to maximize it, but
yeah, then what you do need is a certain threshold on how much safety you can get. But maybe there is an alternative there that says if you just increase that by, you can increase that still by quite a lot and then gain a lot in the other objectives. Or it might not cost a lot in the other objectives to increase the safety margin by quite a lot. Then why wouldn't you do that? So the only reason is because you haven't seen the alternatives. So that's. So I would.
Yeah, but okay.
I mean, so sure.
Other objectives. You can impact the other objectives. So.
Yes.
Transforming a constraint into another objective will perhaps decrease the values of the other objectives.
Yes, but if you take this multi-policy approach, you can see which trade-offs there are. So you're going to get to see the covered set. That gives you a lot more information to select what you prefer.
I guess the other point, especially in this example, if you're not giving all the policies for the human to choose, the machine has to choose its choose. So the machine has to trade off all the different dimensions.
Well, it's probably not the this user, it's probably going to be the designer who's going to choose. Right? So the manufacturer. Or what might also...
But the wheelchair is playing on real time.
Yes, but typically the wheelchair itself is not learning while it's in operation, right? So the planning is, the policy is derived beforehand, offline.
No, you're not learning, you do have a model that you can plan on site. Right? You just say I want to go there and you plan that path. It's not that path was pre-computed for me to go there. There might be more than one path to go there, and someone has to choose that set of policies. What is the best policy? Am I willing to trade off a little bit of safety and get too close to the wall of the wheelchair, or not? Right? And
yeah. So
I think if the planning or learning is happening online, then the scenarios that we talked about at the beginning don't really apply. So either you need to have a human in the loop, which is probably not practical online because it means every time the wheelchair makes a decision, a human has to be involved in that decision. It's probably not practical.
okay.
I guess it's just one point for what Johan was saying. If you put some thresholds and you just use the other cost functions as
that would be one way of scalarizing.
As constraints, then the machine can always find what is the best policy, right? There would be no choice, there would be just one.
Yeah, but that would be so that would be scalarizing. So you say if it's below this constraint, then the value is negative infinity, and else it's.
Yes, but so I mean,
it's a specific scalarization function. There's a lot of ways to do scalarization.
At the highest possible level, you can think of multi-objective planning as kind of like a partial planning process. You're planning without all the information you actually need to do the planning, because that information is coming later. So that means that the planning is inherently incomplete, and later there will need to be more input. The weights will have to come in, and the user will have to be involved. So if you have some kind of online real-time system where it won't be feasible to get that input, then this is not the right model. Then whether the a priori scalarization is natural or easy, you probably still have to do it because you just need the system to be able to make decisions instantly.
Yeah. The other thing that I've discussed, for some recent work on information retrieval, is, for example, if you have a search engine, it tries to derive your preferences somewhere from implicit feedback that you get over a very long time. So it has a covered set over all possible policies, and then by just interacting with you over a very long time, it adjusts the weights. But that's, yeah, so that's partially forthcoming work, but that's also a way in which it can be applied. Then one of the main advantages of multi-objective planning and offline planning is that you pre-compute this set, and then if you have these preferences later, even if you, whether you can tell them explicitly or you have to infer them, then that's the only problem you have yet. The picking of the policy is...
Yeah, I do understand, because the point is, in the end, someone has to choose one policy.
Yes,
and
but
the
that's...
question is, if it's not a human, then you have to find a trade-off between the two.
Yes.
But
that
that doesn't
is
have to be
essentially
human. Like if you think about this mining example, you know, maybe you're doing multi-objective planning because you don't know the price of gold and silver when you make the plan. But then later when it comes to the execution phase, like a bot can just check the commodities market and find the weights and then decide what to do.
Yeah, your prioritization comes from the cost, right?
Yeah, so...
From the price.
Yeah, that's what I mean by cost.
Yeah, but so this is actually the assumption that we always make. At some point, there's going to be an execution phase, and so we have to select one policy to execute. That is always going to happen. So either in this, the undominated scenario, or in the decision support scenario. So it doesn't, but whatever you do, there will always be one executed policy. Any other questions? Then thank you again, and I'll see you around.